Good day, guys. This is question 6 in November 2020 question paper. It's a chemical equilibrium question. Now, it says steam, which is water in a gaseous state, reacts with a hot carbon in a solid state, as we're seeing there, at 1000 degree Celsius according to the balance chemical equation. The equation that we are given there, it's a reversible equation, and we have water in a gaseous state react with the carbon in its solid state, and it produces the hydrogen gas and the carbon dioxide gas. Now it says initially 36 gram of steam, which is water, 36. This is the amount that was there initially. It's 36, and a certain amount of carbon were placed in a 2 cubic centimeter sealed container and allowed to react. We are not told how much the amount of carbon. They told that it's a certain amount that was there initially. Now it says at equilibrium, it was found that the amount of carbon changed by 0.225 mole. Now they tell us at equilibrium, the amount of carbon that remained after the reaction has taken place, it's an amount of carbon that remained after the reaction has taken place is that. Now 6.1, it says define the term dynamic equilibrium. Dynamic equilibrium is a state in which the chemical reaction where the rate of forward reaction is equal to the rate of reverse reaction. Now 6.2, it says calculate the equilibrium constant for the reaction at 1000 degrees Celsius. Guys, first of all, what do we need to do in 6.2? We have to convert the mass of the steam, which is the water, in a gaseous state into number of moles. We'll say number of moles is equal to mass over molar mass. These are the number of moles of what? Of water, which is the steam. And the mass is 36. We divide by the molar mass of water is 1 times 2, which is the hydrogen plus oxygen. Oxygen is what? Is 16. That will make 18. So it's going to be 36 over 18. That will make 2 moles. These are the 2 moles of water that were there initially. Now to calculate Kc there, you must have the concentration. You must have concentration of the reactants and the product at equilibrium. So we have to go to the table in order to calculate the Kc there. Let's go to the table. I already drawn the table there. Now, in the table, what do we have there? We're going to place what we have in the table. Now, in the table, we are given the initial amount, the one that we already converted. It's what? It's going to be 2 there. And the hydrogen that was produced, we do not have. And the carbon dioxide that was produced, we do not have. Remember what they told us in the statement. They said, at equilibrium, it is found that the amount of carbon changed by 0.225. Now, if you're looking at carbon there, even though carbon we're not going to involve in the table, if you look at my table, they are only involved there the gases, right? The solid is not involved in the chemical equilibrium. So in the solid state we do not involve in the chemical equilibrium. Let me leave it like that. What we involve there is gases and aqueous. So the solid and the liquids we do not involve in the chemical equilibrium. They do not change the chemical equilibrium when we change them, the factor that are in those state, right? Now it says that equilibrium, it was found that the amount of carbon is 0.225, right? Now if you're looking at the ratio in the equation there, if you're looking at the ratio of carbon and carbon dioxide is 1:1, right? Their ratio is 1:1. This simply means that if their ratio is 1:1, that means the number of moles at equilibrium is equivalent. So we will say the number of moles, in fact, the change of number of moles of carbon is equal to the change in number of moles of what? Of carbon dioxide, which is going to be what? It's going to be what was the amount is 0.225 mole. So let's place that. Guys, this happens because the ratio it's 1:1. Their ratio is 1:1, so it's going to be the same. So let's place the value there. So at equilibrium, these are the number of moles at equilibrium. This is the number of moles. This is the number of moles at equilibrium. So that this value, we're going to place it here at 0.225. Since, guys, I'm repeating this. Since their ratio is 1:1, there. So if this value is 0.225 at equilibrium, also the carbon dioxide at equilibrium, it's going to be the same value because the ratio is 1:1. So I place that value there, right? So what we're going to do now, we're going to, in this table, since there's a 1 there, I'll just place 1x there. Since there's a 2 there, the mole that balances the equation there, I'll just place plus 2x. Since there's a 2 there, I'll say minus. Since it's the reactant, I'll say minus 2x. So what I'm going to do, I'm going to find this value of x, the value of x there. So let's do it like this. Remember, in the product there, we adding this value plus, we'll say 0 plus x is equal to this amount. So we'll say 0 plus x is equal to 0.225. And then what we're going to do, our x is 0.225, right? So the value of x here is 0.225. Now we have the number of moles there, the number of moles that, which is the change in number of moles there. So here we're allowed to do to take this value of x and substitute there. So what we're going to do there, we'll say 2 times, we have our x there, it's 0.225. So it's going to be 0.45. So our value of x there, let me put it in another color. Our value of x there is going to be 0.45, right? And it's going to be the same value here. It's going to be the same value here. It's going to be 0.45. Since it's 2x and 2x is the same, I was going to do the same thing there. Now we know this is the initial amount that was there before the reaction take place, and this is the amount that was used in the steam. And then now we have to find what is the amount, which is the number of moles that will remain at equilibrium. We will say this amount that was there and minus the amount that is used, and then we'll get the amount. It's going to be 1.55. Yep. And here in the product we're going to add, we're going to say this amount plus this amount. So it's going to be 0 plus 0.45. It's going to be 0.45, right? Now, these are the amounts that were left at equilibrium after the reaction has taken place, after the reaction has reached equilibrium. These are the amounts that remained there. Now, the last E there, it's the concentration. So we have to calculate the concentration using the formula that says C is equal to N over V. Now, the number of moles, will say 1.55 divided by the volume that we're given that this reaction is taking place in. It was 2 cubic decimeters. So the answer is going to be 0.775. Here we'll do the same, calculating the concentration using this number of moles. 0.45 divided by 2, which is it's going to be 0.225. Right, same thing that we're going to do here. It's going to be 0.225. We divide by 2, it's going to be 0.1125. Right, now this is the concentration at equilibrium. We're using this concentration at equilibrium in order to calculate Kc. Now let's calculate the Kc. Our Kc value we calculate by saying Kc is equal to the concentration of products divide by the concentration of reactants, right? That's the standard. Now let's do our case now. What is our product? It's going to be the product of the concentration of hydrogen gas and carbon dioxide. So it's the hydrogen gas. Remember, the hydrogen has the value in front, which is the number of moles. So we're going to put that value there. And then we multiply by the carbon dioxide, and the carbon dioxide, what is the value? It's 1 there, so it's going to be to the power 1 there. We don't have to put that value. And then the reactant, we know at Kc the only value that we're going to involve is the steam. The only compound or the substance that we're going to involve there is the steam. The steam, it's going to be water to the power 2 because it has the value in front, which is the number of moles in front there. Now, let's substitute. I hope you get that. Let's substitute our concentration that we have calculated there. So, the concentration of product, which is, let me do it this way. So, the hydrogen gas, it's going to be 0.225 square. We have the square there, multiply by the concentration of carbon dioxide, which is 1125, divide by the concentration of water at 0.775, right? We punch that in the calculator. When we punch that in the calculator, and I forgot the square there, there's a square. When we punch that in the calculator, it will be 0, 0.0948. Guys, what we need to remember, the Kc value, it has no units because it's a ratio of concentration. This is the ratio of concentration of product and reactant, so it won't have units. So that's the answer that you are required to answer in 6.2. Question 6.3, it says the graph shows how the rate of forward and reverse reaction changes. This graph, guys, is a graph of rate of reaction versus time. Now, this graph, it shows two rates, the rate of forward and the rate of reverse. The solid line indicates the rate of forward and the broken line represent the rate of reverse. Now, guys, if you're looking at the beginning at t0 there, just to analyze the graph at the bit, the rate of forward is that value, which is higher than the rate of reverse. If you look at the rate of reverse there, it's there at the bottom. So their rates in the beginning were not equivalent. So the rate of forward was higher than the rate of reverse. But now as the reaction progresses, there was no product that was formed in the beginning. So if there was no product is formed, that's why the rate of the reverse is there. It's very low. Now, as the product is formed, the rate of forward decreases. As the steam, which is the reactants, the concentration of the steam or the concentration of the reactant decreases, the rate of forward decreases. And as the product is formed, as the concentration of the steam decreases, the product is formed. Therefore, the rate of reverse will increase up until they reach equilibrium. So starting from T1 till the beginning of T2, that's equilibrium. What is equilibrium? It's when the rate of forward and reverse are equivalent. Let's look at T2. T2 there's a sharp increase in one of the reactions. If you look at the reaction of forward, the solid line, there's a sharp increase and there's a slight increase there in the reverse. So the one that has a more increase there is favored. So in this graph, it shows that forward is what? Is favored. Forward is favored. Now, interpreting what is that disturbance there? At T2, there's a disturbance and one of the factors. So that disturbance is a what? Is a temperature. How do we see it's a temperature? We see it's a temperature because the other increases more than the other. If you look there, the forward increases more and the reverse increases slightly there. It's an increase in temperature. And then the system reinstates the new equilibrium again. And now at T3, there's another disturbance there. You see there, they both increases, the rate of reverse and the rate of forward, they increase both. And then they reach equilibrium. And their equilibrium is the same there. That's the new equilibrium. So this, I'm not going to spoil it now. What is it? Let's go to 6.3.1. It says, give reason why the rate of forward reaction, it decreases between T0 and T1. It's 6.3.1. It's because, as I've mentioned there, it's because the amount of steam. What is a steam? It's H2O, the hydrogen oxide, which is the water in a gaseous state, decreases or used up. As the reaction progresses, the reactants decreases, which is the reactants in this case, it's a steam. So the concentration of the steam or the amount of the steam is used up or decreases, or the product is formed, right? Let's leave it that way. 6.3.2. What change was made at equilibrium at a T3? 6.3. They're looking at T3 there. Guys, when they increase both in the rate of forward and reverse, they increase both in the same way. if you look here, the increase in the rate here at T2 is not the same, but the increase here is the same, and it reaches the same equilibrium. So when it's like that, guys, there's an addition of what? Catalyst. Catalyst, guys, in the equilibrium, what it does, it increases both the rate of forward and reverse. But when you are changing one of these factors, CPT, if you're adding temperature, the rate of forward and reverse is not going to be the same. When you're decreasing or increasing pressure, the rate of forward and reverse is not going to be the same. Concentration as well, rate of forward and reaction. So if you change one of those factors, the rate of forward and reverse is not going to be the same. But here, there's no favor here. Both are favored. The forward and reverse are favored, and they are increased both. They increased there. So the rate, so the addition of catalyst, I hope you get that. At T2, the temperature of the system increased. As I've mentioned before, here at T2, if there's one that increases more than the other, it's a temperature. That, guys, I have another video that explains the graph, so go back to that video and listen to that. At T2, there's an increase in temperature. We know an increase in temperature generally favors the system, favors what? Endothermic reaction. So when you increase in temperature, generally in the system, what are you doing? Your disturbance, it's an exothermic, but the system will decrease the temperature and favors endo. That's why we say the increase in temperatures favors exo, because the system counteract what you have done, or the system opposes according to Le Chatelier's principle. Le Chatelier's principle says the system will reinstate or oppose or favors the opposite reaction of what you have done. Okay, 6.3.3, hope you got that. Is the forward reaction exothermic or endothermic? Let's look at the graph again at T2. Now let's look at the favor there. If you're looking at the rate of forward and reverse, the one that is favored is the one that increased more. So the forward has been favored there. So if forward has been favored, and we said before, increase in temperature favors the endo, that means the endo here is what? Is forward. So we'll say it's endothermic. So forward here is endothermic, because looking at the graph, is forward that is favored, and there has been an increase in temperature. So the increase in temperature is what? Is endo. Now refer to now it says refer to Le Chatelier's principle. The definition of Le Chatelier's principle. Le Chatelier's principle tells that if in a closed system there's a disturbance, the system will try to oppose the disturbance and reinstate the new equilibrium. So let's explain that according to Le Chatelier's principle. Now, according to Le Chatelier's principle, one thing that we should mention there that is important, we'll say the favor, we'll have to talk about the favor, right? We'll say the forward reaction is favored, right? Forward reaction is favored. That's what we have mentioned. And then what I've mentioned before as well, we'll say the increase in temperature favors what? Favors endothermic reaction. I already mentioned that before. And for more, that's 2 marks. That's good enough already. That's 2 marks. One. That's 2 marks. But if they can ask you about the equilibrium constant, what happened to the equilibrium constant there? Since you have increased temperature, in fact, in equilibrium, the equilibrium constant is the only factor. Temperature is the only factor that affects the equilibrium constant, Kc, the Kc value. So now if we've increased the temperature, doesn't mean that the Kc will increase, but it can increase, but it cannot increase. So what we look at the concentration of product, because Kc is directly proportional to the concentration of products, right? So if the concentration of product in an increase of temperature increases, that means the Kc will increase, right? Let me leave it there.